Good morning. Hello, Biology 2, Human Anatomy and Physiology. Once again, I miss you guys. We were talking quite a bit about the action potential, the common language of the nervous system. Today, I want to show you some videos which are really cool in terms of giving you a good, solid grasp on what's going on with a nerve impulse. If you understand how action potentials work, then you can understand how to manipulate action potentials. In other words, if you certain drugs are going to be nerve inhibitors or nerve stimulators. How does a drug inhibit a nerve so you can go to the dentist and not just be screeching with pain the whole time you're getting that root canal? It's intimately tied to how an action potential works. So if you understand the basics of the action potential, then you'll understand the basics of a nerve inhibitor or a nerve stimulator. So here we have a neuron, and well, let's see, just a few things before we watch the video here, just a few things. Notice all the connections. We have lots of synapses here. So a synapse is going to be that connection between nerve and nerve or nerve and muscle. Of course, the neuromuscular junction has a synapse, and that's going to, the nerve's going to release the famous neurotransmitter acetylcholine. As you're going to see, there are many different neurotransmitters within the central nervous system, but there's only one at the neuromuscular junction. So we are going to talk about some of these other neurotransmitters in a little bit. So notice here would be a synapse. Oops, let's do this. Here would be a synapse. Notice, let's see, there's another synapse. So these gaps are going to be measured in microns. So we're talking about a millionth of a meter in terms of the distance. And within that synapse, that's where the neurotransmitter is going to be released. Well, here's the cell body or the soma. You're going to find the nucleus in here. Notice this region is, here's the axon. And again, the axon is going to carry nerve impulses away. So there's my nerve impulse moving away from that soma or cell body here. Of course, axons send nerve impulses away. So dendrites are going to be sending the nerve impulses towards the neuron. So we could have a dendrite, and here's my nerve impulse moving in this direction. Of course, this cell body here, the soma, is going to essentially be receiving lots of communication and then kind of summing up that information, chemically, so to speak, summing up that information, and then eliciting a response based on the information that it's taking in. Well, all right, so let's watch the video now. Clean this up here.
The cell body, plasma membrane extensions called dendrites, an elongated fiber known as an axon, and an axon hillock, the trigger zone that releases a nerve impulse. The axon hillock maintains an excitation limit or threshold, which determines whether or not a neuron will generate a nerve impulse. A nerve impulse is an electrical signal conducted by a neuron, causing a response in another neuron or target cell. When a neuron is at rest, its membrane is polarized because there are more positive ions outside the cell and more negative ions inside the cell, which creates a charge difference across the membrane. Active transport mechanisms called sodium-potassium pumps carry more sodium and less potassium ions across the membrane to maintain this charge difference. Even in a resting neuron, there is the potential for the charge difference to create an electrical current. This is called a resting membrane potential. When an electrical current flows through a dendrite. This is called a local membrane potential. When a dendrite detects a stimulus, a sodium channel in its plasma membrane opens and lets sodium into the neuron. This influx of positive ions reverses the charge across a particular section of the membrane in a process called depolarization. To repolarize the membrane, potassium channels open and release potassium out of the neuron. Nearby, a sodium-potassium pump transports excess sodium out and brings potassium in, which restores the resting membrane potential.
Have no fear.
The flow of reversing charges along a dendrite's membrane produces a wave-like electrical current toward the neuron's trigger zone. If the strength of the current meets or exceeds the threshold at the trigger zone, an electrical signal called an action potential or nerve impulse will occur. In a nerve impulse, the trigger zone sends an electrical signal down the axon.
Notice that's a myelinated axon with the Schwann cells wrapping around.
Or to a target cell membrane.
Neuromuscular junction right there. All right, and now let's go through one more. So just look and listen and get the concepts here. Notice high sodium out, high potassium in. Notice the different colors here. So here we have the sodium. Here we have the potassium. I think that's the right color. No giggling. No giggling out there. So yeah.
When the cell membrane is at its resting membrane potential, the activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
So I want you to listen carefully and follow the reasoning here, because if you have a decent grasp on what an action potential is, then you can have a decent grasp on the effect of certain pharmaceutical drugs are going to have on nerve stimulation or nerve deadening. Okay, well, here we go. Nothing new here. We've got the negative 70 millivolt resting potential of the nerve. Again, this is going to be the axon. What we're talking about for the axon would apply for the soma or the cell body as well. Anyway, notice at the start we have high sodium ion, so there's my positively charged sodium, quite a few of those. Notice on the inside of the axon we have high potassium in a different color. Note that there is a potential difference there in charges. Even though they're both positive charges, there is a difference in charge here, more positives here than in here. Also note the negatively charged anions. Sum all this up and the potential difference is approximately negative 70 millivolts. Well, what would the effect be of a certain drug that would increase the permeability of the nerve cell or the axon? What would the effect be if that drug increased the permeability to sodium ions? How would that affect the cell? Would it make the cell more excitable? Would it make the cell harder to excite and shoot off a action potential? Or would it have no effect? I want you to think about that for a moment. Come up with an answer. Write it down. Write it down. I need to see all these notes, by the way. Take a picture and send it to Google Classroom. No credit unless it goes to Google Classroom. Do it. I'm back. So here's our drug X. So let's say that this drug here, get a different color, let's just call it drug X. So here's drug X. Drug X is going to increase the permeability of this membrane to the sodium ions. So, drug X comes in, it's going to have its effect. Notice drug X is going to allow these sodiums to seep in. So here's some sodium ions creeping in now. A big question would be, what effect does this increase in positives have on that negative resting potential? Well, obviously the negative 70 is going to start creeping, moving towards 0. It's going to get a little bit higher and a little bit higher. If you recall, nerves have threshold potentials. That threshold potential might be different for different types of nerves. Let's say that the threshold potential is negative 55. So resting potential is negative 70, threshold's negative 55. If we're graphing this, we would see that we're starting here at negative 70 millivolts, and at resting, here we go. But as the sodium ions begin to move in because of the effect of drug X there, this is going to start moving up. Now, as more of these positives come in, we're going to approach this negative 55, which is threshold. Remember, once you hit threshold, the nerve's going to fire. So, here we go. As soon as we hit here, there's threshold. There we go. Notice maybe get another creeping in here. And at this point, the nerve is going to fire. And we're going to get an action potential. And then we're going to get the same scenario of events that we've been talking about. The sodium ion gates open up. Sodium's going to rush in. Membrane becomes depolarized. Here's sodium rushing in. Then potassium is going to rush out. As potassium rushes out, we're going to get more and more negative here. We're going to overshoot our negative 70, then sodium potassium pump, and we're going to reestablish a, let me make that a little bit lower here. We're going to reestablish the original resting potential there. Again, right here is where you reestablish the original ionic concentrations of sodium and potassium. So, the sodium ions rushed in at this point once we hit threshold, and then of course the potassium ions rushed out, so we'll make that blue. So potassium ions rush out. And we're back to where we started here. So what effect did this drug have? The effect of this drug, rather, would be to stimulate the nerve. So this would excite the nerve, make it easier to excite. So this would be some sort of neurostimulant would be having this effect. Again, if you're at resting and it's negative 70 and positives come in, you're at negative 70, positives are coming in, so that's going to throw the resting towards zero now, towards threshold, making that nerve more excitable, hyper excitable. All right, next question. What would be the effect of a drug that would increase the permeability of that nerve cell to chloride ions, to Cl- ions? Would that excite the nerve? Would that inhibit the nerve, or would that have no effect? So now this drug is allowing Cl- to move into the nerve cell. Give that a shot. All right, so the effect of a drug, let's call it drug Y. Y, I don't know. Let's call it drug Y. And what is, if that effect is to increase the permeability of Cl- so that, let's say, more Cl- are going to enter the nerve cell or the axon, what effect is that going to have on excitability of the drug? Okay, so here's our drug Y. And notice drug Y, let's extend this out a little bit. Drug Y is going to increase the permeability of chloride ions. So we have Cl- out here on the outside. We'll draw quite a few. Well, if you recall, we did talk about genetic diseases, and the cell is constantly moving chloride ions in and out based on osmotic gradients and whatnot. So maybe you remember when we talked about cystic fibrosis, where we have this transmembrane protein which allows chloride ions to flow back and forth in the proper concentrations. When that protein channel for chloride ions is faulty due to a genetic glitch, then we disrupt the concentration of chloride ions on the inside relative to the outside, and it leads to profound effects. And this is CF, cystic fibrosis. Well, anyway, enough on that. Let's talk about chloride ions. Let's talk about the effect of this drug moving to the inside of the nerve cell. So here's my drug Y. Notice that that's going to increase the permeability of the sodium, or these chloride ions rather. And put another one in here. So notice the Cl- are moving to the inside of the axon. What effect are Cl- ions going to have on that resting potential? Well, isn't it going to make the resting potential more negative? It's going to reduce the resting potential, is going to go down. And if you go down, you get further away from that negative 55, that threshold. So let's look at it on a graph. Again, we have millivolts here. We have time in milliseconds here. Notice, here we are at resting. So I've got a different color, and let's say we're following that same pathway. We add the drug at this point. So now we add drug Y. And notice we're having the Cl- move in, So here's resting, and what's going to happen is we're going to decrease this value here. So now we're going down because of the negatives, the negative effect on that negative 70. So look at where we are now. Now maybe we're at, let's go with 85 here. So negative 85.0 millivolts. And then notice at this point here, we've really increased the gap between our new resting. So notice that's new resting and this negative 55. Obviously now, it's going to take a much stronger stimulus to get this negative 85 to reach threshold up here at negative 55. So notice, let's stimulate this nerve now with a typical stimuli. Notice this is coming in, this is coming in, this is coming in, this is coming in. Now we're going to be moving back up closer to threshold here. So we're getting there, but it's going to take a much stronger stimulus to get to negative 55. So we're going to have to really increase the magnitude of this stimulus to get more of these to move to the inside. And when that does eventually happen, if we do make it up here, then of course we can fire again and we get another action potential. So the effect of the Cl- is going to be to deaden the nerve. What if we were to inhibit the activity of the sodium-potassium pump? Well, if we look at, let's see here. If we look at this original, let's go with the original graph here. If you recall, right in this region, that's where the sodium-potassium pump has its effect. Okay? If we inhibit that, what is that going to do to the ability of that nerve to fire? Well, this would be a typical mechanism for a pharmaceutical drug that would be used at the dentist. We're going to inhibit the sodium-potassium pump, so the nerve simply cannot fire if it doesn't have the proper concentrations of sodium and potassium. So we're kind of getting into a little bit of pharmacology here, which is interesting and important. I hope all is well. Take good notes, good notes. Picture, Google Classroom. Everybody, have a good day.